how an example of what I would call an in-spiral rain-down consistency check. So an example of that is the area increase law. And then comes sort of the main part of the talk, which is the, again, with the rain-down, which is evidence for the higher overtones and what can we say more about that from the point of view of the black hole itself. So apart from this higher overtones part, that is the heart of the whole talk. So that's where new results are. The rest of it is mostly older results. And then finally, we have conclusions. Okay, so let's begin. So I think all of you must have seen this at some point or the other. So this shows the data from the first detection. So this is data from the two different detectors, and compared with, in the second panel, simulation from numerical relativity. So I don't want to talk about the other two panels, so just to focus on the first two. So what you see clearly is the feature of the waveform, which is you have initially, so the longest phase is this in spiral phase, in which you have oscillations of increasing amplitude and increasing frequency. Then you have the burst of radiation at the merger, and then you have the final part, which you think is a ring down. And the way you think about these things is that in the first part, you have these two black holes which are orbiting each other. They come really close to each other. They merge, which is then the high amplitude part. And then the final black hole then relaxes to a equilibrium curved black hole. So that is the final ring down portion of this. So that's all very heuristic. So now the question is, how do we actually compare what's happening at the black hole itself? And so whenever you say that you have two black holes orbiting and merging, you're talking about sort of the space-time near the black hole horizons. While these observations are, of course, on Earth, where we are very far away from the source. So you need some way of correlating what is happening in our detectors, what we are observing, to what is happening at the source itself. So this relates, for example, to when do you want to precisely say there's a transition from in-spiral to merger, or transition from the merger to the ring down, and so on. So that is sort of the broad theme. And then I just want to sort of make a little digression and just talk about the existing detection so far. So in the catalog paper from the LVC, so sometime last year, so they reported these binary black hole events, starting from the very first one. So these covered the first two observing runs of the LIGO-Virgo detectors. And then there was, of course, also the neutron star merger. And they were the more recent, the O3 detections. So these are the three detections from 2019. And the data from O3 is not public yet. So, but the data from the first two science runs is entirely public. So those can be analyzed by non-LVC groups. And in fact, groups at Hannover have reanalyzed the first and the second observational runs. So results from that are again available in these publications here. So this is to say that there's a large amount of data that's available that's really open. So for all the people who wanted to get into gravitational waves, all the students and everyone. So just keep in mind the huge amount of data that's going to be available for doing analysis independent even of the LVC. So one of the results of these reanalyses, for example, was that this event called 15-10-12, which was in a sense, the October event from 2015. So that was promoted to a bona fide detections. And in addition, there were many sort of not highly significant events, but which were marginal. Those were also released. So why did we do that? So collection of these events might be significant collectively. So in other words, from a collection of n number of these events, you might say that, well, some subset of these might be signals, even though you cannot say which of these they are. Or you might want to find coincidences of these marginal events with other events, by which I mean events not gravitational waves, so could be some electromagnetic triggers. So that coincidence might make these events more significant. So that's a reason for releasing even the marginal events in this case. So in addition, there were also events which were not found by the original LUC analysis. So examples of these are 170121, and these two others reported here. And in addition, this paper here also reports parameter estimation results for these and more sub-threshold events. So coming to these new events not found by the original analysis, this were in fact first reported by the Princeton group. So that is this slide here. So this is in a number of papers going back to early 2019. So they reported 3 new events with high significance in O2, and then 3 marginal events. Again, the marginal events do not agree with the other catalogs, so I think that's always going to be the case in marginal events, but at least the high significance events do agree with the other analysis. Right, so and then as soon as the O3 results become available, then of course similar analysis will be performed, and hopefully further events will be discovered even for those cases. So now let's go back to the first detection, and then to the binary black hole signal morphology in general. So as we saw, the observed signals show these 3 regimes of the mergers. So we have the in-spiral, which is this oscillatory part, which of increasing frequency and amplitude. So that is well described by PN theory. So then we have the ring-down portion, which is the very end, which is the part when the final black hole relaxes. So that part is well described by black hole perturbation theory. And then in the middle, we have the merger, which is the highly nonlinear part involving the formation of the remnant black hole. And as you've heard in a number of talks so far, so different tests have been proposed for these different regimes, and there's also consistency text between them. You heard a lot about the in-spiral, the parameterized PN test. You heard a lot about the ring down and black hole spectroscopy. I'm not sure if I missed maybe some talks. So there's also IMR consistency check, which I will talk about briefly in this talk. So this is a test of consistency between different portions of these signals. So for example, between the pre-merger and the post-merger signal. And of course, there's other test of consistency also possible. So let me talk briefly about this consistency checks. So the basic point is that any prediction of the final state from GR, so you could test that in principle. In other words, what you have is given the initial configuration in which you have some masses and some spins and let's start off with 2 black holes far away with this configuration, but gravitationally bound to each other. So then based on either analytic calculations or numerical simulations, you could compute, for example, the final mass of the black hole or the final spin. And then if you can independently measure these final mass and final spin or any of the other quantities that these calculations might tell you, so that you can think of as a test of GR. So an example of this is the area increase law. It's a nice example, I think. So this is true in full GR, so it's nothing perturbative about this. It's true in full nonlinear GR. It's an exact result. So it says that the black hole always has to increase in area, the horizon has to always increase in area. So therefore, if you independently can measure the final area, so for that you have to assume that the final black hole is curved. So given the final mass and the final spin, you can calculate what the area is. And the same thing for the 2 initial areas. So then you can convert this to a test of GR. So now the test might be very stringent or not, that's a different question, but in principle, this is a test of GR. And moreover, there's a test which really probes the merger, because it's only in the merger that you really expect the area to increase significantly. So you can think of this as a test of nonlinear GR in this sense. So again, just a short historical note. So in fact, the very first estimate for the energy radiated in a binary black hole merger, so that was based on the area increase law. So this goes back to Stephen Hawking in 1971. So you start off with 2 black holes very far apart. Let's say the initial masses are M1 and M2. And then the final mass of remnant, so technically the final the bonding mass, so that's let's call it MF. The area increase law implies that you have A1 plus A2 lesser than or equal to AF. And furthermore, if you assume that the black holes are initially Kerr and finally it's also Kerr as well, so then there's a formula for the area given the masses and the spins. So then you get this inequality, which is shown here with M1 square and so on. So you can convert that to set a limit on what you might call the efficiency, which is how much mass is lost due to radiation. And then, if you set the masses to be equal and you set these tend to non-spinning, then you get a limit of 29% for this efficiency. This is, of course, enormously large and much larger than what we actually see. This tells you that this is not the most stringent test that you can do. But nevertheless, it does provide a very clear inequality for the in this sense. So now I'll come back to this in a minute, but let me now go on to the basic test of GR that we want to do. So the very first test of GR that you want to do is, why do you think, given the signal that we are seeing, why is this why do you think this is a binary black hole? Or more precisely, why would you think that this is a very massive object which is very compact? So now what I'm going to talk about is a very basic back-of-the-envelope calculation. This is, for students and all who are starting to get the subject. So this is going to demystify the whole thing. So you might often hear about a lot of complicated Bayesian inference and complicated software for doing this analysis. So, but this is a case in which you could answer this basic question of, GR predicts that there are black holes. Does this data tell us to expect that there should be black holes in our universe? So you can do this very simple math I'm going to tell you about in the next few slides, and which requires nothing more than literally you can take graph paper and a ruler, let's say. So what you can do is the following. So you can see that the signal frequency increases from about 35 to 150 hertz over about 8 cycles. So by that I mean that if you look at again the signal and you simply look at the oscillation in the in-spiral part, and you simply look at the period of these oscillations, you can estimate what the frequency of these would be at any given time. So based on that, you can do this calculation I'm telling you, which is that calculate the frequency, and then you estimate the frequency goes from about 35 to 150 hertz over about 8 cycles. So what is it that could lead to a signal like this with increasing frequency, increasing amplitude? A plausible explanation is a binary system. And then for a binary system, this is the only result you need from PN theory, which is a leading order calculation. This tells you that the rate of change of the frequency of the system is given by this equation here, which depends on f to the 11th hertz. And you get this combination of the masses M1 and M2 combined in this very strange way to give you what is called the chirp mass. So f dot depends upon f to the 11th hertz, and there's a prefactor depending on the chirp mass. So you can just integrate this. You can say f to the minus 8 hertz must be the linear function of the time. And therefore, in this linear function, the coefficient I'm putting in front can tell you what the chirp mass is. So you can actually do this. So you can actually take a bit of graph paper or write a little Python code for finding the zero crossings of the data here, and then you can estimate what f to the minus 8 thirds is and what the values of different times are, and you can plot them in this graph here. So the green dots refer to f to the minus 8 thirds for both H1 from both Hanford and Livingston as a function of time. So the slope of this graph you can just put a straight line to this, and the slope of this straight line will tell you what the chirp mass is. So the green one is the best fit. The blue one corresponds to about a chirp mass of 30 solar masses, and the red one to 40 solar masses. So just based on this, you get that the chirp mass was something between 30 and 40 solar masses. Okay. And then just as a plausible thing, so if you say that the masses are exactly equal, then the total mass, you can just do a little algebra, and total mass will be 70 solar masses. And then, well, let's come to how compact these objects are. So you know that if you believe it's a binary system, and we have an orbital frequency of 75 hertz, which is different from the gravitational wave frequency, 1/2 of that. So then you can just apply Kepler's third law, and you can say the radius of the orbit the separation of the orbit must be 350 kilometers or thereabouts. So the two objects need to fit into this orbit. So I must have the sum of the radii of the objects being lesser than this separation. And then you can say that the objects have to be really very compact. So they have to be less than, about 100 kilometers or thereabouts to fit into this orbit. So that really tells you these are really massive compact objects, and the only plausible explanations so far that we know are black holes. And you can relax many of these assumptions. You can make the masses to be different. You can include spins and eccentricities, and the same argument goes through more or less. So this is sort of a very basic calculation you can do from the data that tells you that these are really massive compact objects and most likely than black holes. So this is like the first very basic test of GR that you can do. And of course, all of this, you might object is that this is not really within GR. We're not using any, the proper distance between the black holes and things like that, but fine. At least this gives you the right answer. If it did not, then you would really worry about it. So as I said, this is not really a proof because it doesn't include many of the higher order corrections to the basic PN calculations. It doesn't use these coordinate-independent quantities, but still, it's a useful check. And we really would have been worried if this had not given the approximate answer. So now let's go to, again, a simple analysis, but not as simple as this one, but somewhat more sophisticated. So this was a plot that has been shown numerous times over the last 2 days. This is a result of the ring down part. So since this is going to be important for this talk, I'm going to describe in some detail as to what was done here.
Sorry, Badri, can I interrupt you?
Yes, go ahead.
The previous slide was still about in spiral. Yesterday we heard Vito Cardoso. Vito Cardoso was talking about boson stars and graphite stars and so on, which don't have a horizon, but could actually give the same signal. In addition, they could have echoes and so on. That's a different matter. So you can't rule those out yet, right?
Yeah, so this analysis wouldn't rule those out. You're right. So all this tells you, as I said, is really that it's a massive compact object. So I can talk about the echoes, and I really don't believe they're there. So that's a different talk altogether. And boson stars and things like that, I have my biases, but that's just my opinion, yes. But that needs a more complicated analysis to rule out. You're right.
Okay, thanks very much. Yeah.
Okay, good. So let's now go to the ring down. So what was done here was the following. So let me just go back to this the data here. So can you see my cursor?
Actually, no, actually.
Okay, good. So then what I'm going to do is I'm just going to hopefully say, and then you can understand what I'm trying to, where on the slide I'm referring to. So if you look at, for example,
the cursor is very small. If you can increase the size somehow.
Yeah. I think I can see now. It's a bit small.
Okay, this will take me too long. I'm just going to try to say in words what I want to say, and hopefully that becomes clear. So what you want to do is look at the top left panel, so the red one, the data from Hanford, and then look at the last part of that, and you believe that the last part represents the damped sinusoidal oscillations in which the black hole is relaxing to its final equilibrium state. So essentially, you want to fit the last part of this data with a damped sinusoid. So an exponential amplitude and then an oscillatory term. So now the question is, at what point do you want to start that fitting? So this is the function I described, which is an exponentially fall-off amplitude, and the sinusoidal function. You need to sort of a start time for that. So then, depending on the start time, we'll get different results for what the frequency and the damping time of this oscillation are. And the same applies to the data from Livingston as well. So if you want to look at the top right panel, the same analysis can be done with that. So what is done then in this plot is the following. So you start from the peak of the strain amplitude, and you measure time with respect to that. And then you say that at a given start time after the peak of the amplitude, we want to try and fit this damped sinusoids, and you want to find the best fit values for the frequency and the damping time. So what is shown here are sort of the contours of, I think, the 90% probability for the frequency and damping time for different choices of this starting time that I mentioned. So the green contour, for example, refers to 1 millisecond after the peak. The next one is 3 milliseconds, then 5 milliseconds, and then 7 milliseconds. And what is also shown here is the solid dark line, which is the shortest, smallest contour of all. So that's a prediction based on the initial parameters that you saw. And then that is turned into a final mass and spin, and then therefore to a final frequency and damping time for the dominant Quasi-Normal mode for the random black hole. So then you see that if you were to do this matching 1 second after the peak, the green one, that does not agree with the black one. But as you go later and later, you do get agreement with the black contour, but the error bars really become quite large. So for example, if you go to the contour at 7 milliseconds, that does agree with the black one, but it's really doesn't have that much information, and the error bars are quite large. And this is because the later you go, the less data you have, and therefore the errors are correspondingly larger. So you might say that starting from between 3 and 5 milliseconds is probably when the black contour agrees with this simple analysis for the ring down. And then if you have in mind the scenario that when the black hole is initially formed, it is highly dynamical, it's not close to its equilibrium state, so then nonlinear effects are important. So therefore, you would not expect this simplistic analysis to agree with the black contour. It's only a little bit later, so between 3 and 5 milliseconds, that you expect to get agreement. So you get consistency with this scenario, but of course you can't prove it. So that will be the focus of the later part of this talk. But let me just summarize these results here. So this analysis suggests that the black hole has reached equilibrium roughly about 5 milliseconds or a little bit before after the peak of the signal. If you convert this to geometric units, then you get a number like 15 m in geometric units in terms of total mass of the system. And then you ask yourself, well, is this what you expect from any other calculations, numerical, analytic, or otherwise? And in fact, as it happened, it's a paper by Kamaretsos and Satya and others who showed, in fact, that this is that this was consistent with this observation. So what they found back in 2012 was that the frequencies of the different modes of the signal, of the gravitational wave signal, become consistent with the Q and M frequencies roughly about 10 m after the peak of the luminosity. So I won't go into the detail of luminosity versus the strain, but just imagine that is roughly consistent with this observation that I just mentioned here. So far everything looks consistent. So then the question is, can you think of this as a way to quantify the end of the merger and the start of the ring down based on observation from the data? So that is really quite an exciting prospect. So now let me go back now to the area increase law, and I will discuss the area increase as a digression here, and I will come back to the this ring down analysis after this. So now, based on, let's go again to the first detection, which was the 5914. So based on all the complicated parameter estimation, not the simple one that I talked about, so something much more sophisticated. So you can compute sort of the initial masses and initial spins, and then based on sort of calculations from numerical simulation, you can predict what the final mass and the final spin would be. So now you might think that, well, based on this analysis, based on M1 and Chi1, you can compute the initial area for the first black hole. Based on M2 and Chi2, you can compute the area for the second black hole. And based on MF and Chi-F, you can compute the area for the final black hole. And then, well, you might expect that, well, the final area has to be larger than the two initial ones, and that is true. But this is not really a test of the area increase law, by which I mean that this procedure by which you obtained MF and Chi-F from the initial parameters, that is based on calculation within GR. So obviously that must be something which satisfies the area increase law. So it must be that if you calculate the final area in this way, then you will always get consistency. So there's not really a test of the area increase law, it is simply a tautology at this level. So what you really need is an independent measurement of the final mass and the final spin. And based on that, then you could hope to actually confront the area increase law with observations. So this is then the basic idea. So that goes back to, in fact, an idea by Scott Hughes back in, I think, late 1900s. So it is simply that you measure the masses and the spins of the initial black holes from the spiral analysis, and you measure the final black hole mass and spin based on the ring down analysis. And then from both of these, you compute the initial and the final areas, and then you can really check if the area increase law is satisfied. And in reality, what you will obtain are distributions for the change in the area, and then you can simply integrate that distribution between for all negative values, and then that tells you the probability that the area is decreasing, and that's like quantitative measure of how much you can violate the area increase law. So yeah, so it turns out that most of the area increase law, in fact, happens during the merger. So ignore that little thing in brackets. I'll talk on next Monday, so it doesn't apply to this talk. And you can, in fact, check in all numerical simulation that the area does increase in the in-spiral phase, but only very, very slowly. So it's only the merger portion that has really a significant increase in the area. And in fact, if you believe that one place to look for deviation from GR might be some nonlinear aspects of GR, then in that sense, this is quite a promising way to look at it. So, and of course, you also want to do the other thing, which is you want to measure the initial parameters accurately, you want to measure the final parameters accurately, and you don't want to be biased by the merger. So what you want to do is for the initial inspire analysis, you want to end that analysis as far away from the merger as possible. And similarly, for the ring down analysis, you also want to sort of start the analysis as late as possible. There's a trade-off, though. I mean, so for example, for the ring down later you go, the worse your systematic errors become. The worse statistical errors become. So there's a trade-off between sort of biases from the merger and between statistical errors, so that you got to quantify. And also, you also assume in this that things like scar location or the extrinsic parameters depend basically on the propagation of gravitational waves. So that is essentially the, if you like, the bandwidth of the observed signal within the detector. So that's its scar location. That you assume is exactly as predicted by GR. So that you don't touch with. So in other words, you would use, in practice, you would use the results of an unmodeled burst search to get scar location. And then you can do this analysis of, choose what is the endpoint of the inspiral and what is the start of the ring down based on different detailed analysis, which I won't talk about here. Right, so just to give an example of this, so based on the criteria we had for looking at the posterior distributions for the masses and the spins, and similarly for the ring down frequency and mapping time, you can obtain sort of a rational way to end the inspiral and to begin the ring down. So this shows an example. So this is the blue part. So the dark red represents the full IMR waveform. It's in this case a numerical simulation. It's really a waveform from an NR simulation. The blue part represents where we decide to cut off the inspiral. So that represents the portion where we're getting the initial parameters from, and the orange portion represents the part where we're getting the ring down analysis, the ring down parameters from. So then based on this initial and the final parameters, then you can go ahead and apply the test that I mentioned. You can compute the change in the area and then check if the area increased law is satisfied. And in this example here, we set the numerical simulation to be at equal masses. So this was 235 solar mass black holes, and the final black hole would have a spin of about 0.69. And in this case, then based on the numerical simulation, you expect the ratio of the final to the initial area to be 1.56. And this is something you can check now based on this strategy that I mentioned. So this shows an example result. So here, on this graph, the x-axis is the ratio of the final initial area. So if AF upon A would be exactly 1, that is 2 to the 0. The vertical line in red is what we expect from GR. And the curve in yellow tells you what the prior distribution in this quantity is. In practice, the prior distribution was uniform in the frequency and damping time and the initial masses and spins. So that translates into this particular prior for the this quantity F upon AI. And then the histogram in dark blue, that is what you expect from O1 sensitivity. And then as the detector improves more and more, so by the time you reach LIGO design sensitivity, that's the light blue curve. So then you can really hope to really constrain this area increase law to a reasonably good confidence. So this is this ongoing work. So we can apply this to actual data, and this is sort of an example result based on simulation that I'm presenting here. And the same thing, we can convert that to sort of the change in the area divided by the change experience. So that's maybe a little bit more transparent, but in any case, it's the same information as in the previous curve. Okay, so this for me is an example of ring down inspiral consistency check, and this is there's other versions of consistency check that you can do, and this is just one of them. And you could do a similar test for the final mass, if you like, or the final spin, and I expect it would get also interesting results. Okay, so now let's go now to the main part of the talk, which is the ring down analysis. So just to now recap the basic framework. So like most physical systems, if you have a black hole which is perturbed away from its equilibrium state, you expect it to emit damped sinusoids and to reach equilibrium. So, and you expect the signal that you see from this to be a sum of this form. So it's a sum over n, l, and m. You have amplitudes and you have a complex frequency in the exponential. And the important part is that we have three different quantum numbers, which is first we have the n, which is the overtone index. We have L, and then we have M, which are the angular quantum numbers. And then the important fact is that for a curved black hole, these frequencies are parameterized just by the mass and the spin in standard GR, ignoring electric charge and so on, which you don't expect to be relevant for astrophysical black holes. So therefore, it's easy to see that if you observe that multiple quasi-normal modes, then you can actually do a stringent test of GR. There's a long literature on this topic. I'm just listing a few here. But this to me is a promising way of testing an important aspect of GR without requiring any alternate theories of gravity. And of course, in practice, the details of this depend upon this question of when do you want to start the ring down and how loud these amplitudes are expected to be, and depending on the initial configuration, things like that. So there's a recent study we did on sort of how likely is it that in fact we will detect multiple ring down modes. So from the previous analysis I mentioned to you, so far things were consistent with just the dominant quasi-normal mode. And in this analysis, we ignore the higher overtones. I'll come back to that in detail later. But for this population study, we ignore the higher overtones. And you simply ask yourself, how likely is it that given what we know about the present populations of binary black holes in our universe, how likely is that you will have something that is asymmetric enough to merge and to produce a detectable signal with multiple ring down modes? So as I said, to get multiple ring down modes, it's better to have asymmetric systems, but then these are also less luminous and also less likely to be seen. And then this study then showed that in fact you have to wait at least for the next, I would say, 10 years. So, but the expectation is that by the time you reached the Einstein telescope with the third generation of detectors, you will be able to find such signals reasonably regularly. And if this sort of test of GR works out, then this will lead to a robust test of fundamental GR predictions. So now, again, going back to this analysis, as I said, the important point here is that we see here a transition between what we might call the merger and the ring down happening at roughly 10 M after the merger, or between 3 and 5 milliseconds in this for this particular event. Okay, so this we already talked about. So now comes the recent work by Max Easy and Giesler. So these are the references I'm quoting here. So these in fact showed that quasi-normal modes can describe not just the part after like 10 M, but even right starting from the merger. And what they showed here was that if you include the higher overtones, which so far we didn't do, then in fact you can fit the signal right after the merger by including enough overtones. So now the question is, okay, that's interesting, but is there something else that you can see in the whole system, at the black holes, for example, where similar effects are possible? So in other words, if I look at the black hole horizon, then it is already known pretty well that if you look at the black hole horizons after the merger, after some time, you can actually see oscillations connected to the fundamental QNM frequency. But then the question is, if you were to push that and go towards the merger a little bit more, would you in fact see evidence for higher overtones there? So this is a different aspect of this part. It's not looking at the gravitational wave at infinity, but it is looking in fact at the behavior of the black hole horizon itself. And if in fact you can see evidence for these overtones in that context. And if you do, then that is strong evidence, in fact, that this analysis is correct, and this really improves the prospects for black hole spectroscopy. So now to explain this, I need to go back and explain what we did numerically. And to motivate that, I'm going to show you this cover from Science back in the end of the Black Hole Grand Challenge project. So this shows the event horizon for two black holes. So in this case, these are this head-on collision of two black holes. And this is one of the first time they were able to numerically find the event horizon. And so this really this is a nice way to visualize what is happening in a black hole merger. I have two black holes that come towards each other and make a final black hole, and the event horizon shows this typical pair of bands structure. So now in our numerical simulation, we would like to do this, but in practice, this is not really practical because event horizons are in fact not so useful in our case. So even though the event horizon, it has a very nice property that it provides a continuous link between the initial and the final states. So this tells you exactly how you have two disjoint black holes which merge into a final black hole. But in fact, the event horizon is not useful for computing the areas, the masses, and the spins during the merger. And there's a detailed sort of talk I could give just for that, but for the moment, just take it from me that the event horizon in terms of causality, so which make this analysis difficult during the merger. So one example of that is to understand how does the event horizon grow. So the picture that you have in mind is that the reason you have an increase in the area for the event horizon is that you have radiation and matter falling into the black hole, which causes the black hole to grow, and that is what explains area increase law. Well, that you might think is true, and in fact, there's a paper by Hartle and Hawking from 1972, which in fact shows this, so which shows that how fluxes and physical quantities evolve perturbatively on an event horizon. But unfortunately, the problem is that this is a purely perturbative calculation. It's not valid in the merger. So in other words, if you want to generalize the Hartle-Hawking calculation to the merger, and you want to understand exactly how an event horizon grows, then you cannot apply this. And this is something fundamental to what's the properties of an event horizon. So now, what do we do? And the solution, which is usually been applied in numerical relativity, is that you use what are called marginal trap surfaces, and you can, so I'll explain what they are in a minute. So these are sort of replacements for event horizons, and I would argue much more better behaved and easier to compute and to understand. And in fact, it is already known that you can locate these apparent, what they call apparent horizons, for the initial two black holes, and you get two disjoint apparent horizons. And then at some point, these apparent horizons get close to each other, and then numerically you can't find them. And then, but fortunately, there's a common black hole that forms by the time. So then you can forget about the individual black hole, look at the common apparent horizon, and that is the thing that settles down to give you the final black hole. So now what we want, in fact, is a replacement for this picture for the event horizon based on these marginal trap surfaces. And this would then provide you the benefit that once you have this, then you can really track physical quantities across a merger in a very well-defined and mathematically rigorous way. So first of all, what are marginal trap surfaces? It's quite straightforward. So these are closed spherical surfaces. So spherical topology does not mean that they have to be exactly spherical, so they can be highly distorted. But they have to be closed. And the condition is that the outgoing light rays from these surfaces have to have zero expansion. So in the case when you have the outgoing expansion, which is the theta L, so I'm assuming that the notation is that the L is the outgoing null normal, N is the ingoing null normal. So for a trap surface, both of the expansions, so which tells you the rate at which the null geodesics along L and N, they are expanding or converging. So that tells you what the expansion is. So if both the expansion are negative, then you have a trap surface. And the important condition for us is that one of the outgoing expansion has to be zero, the theta L has to be zero. So that is the surface that we're looking for here. So as I said, so there's been these surfaces have been used quite frequently in numerical simulations to locate black holes and to understand them. And recently, we've done a lot of work on improving numerically how distorted these surfaces can be. So now, in fact, we claim that we can find extremely distorted surfaces, even surfaces which have things like self-intersections, and we can track these all the way through the merger. So I'm just going to present an example of this. So this is an example of a head-on collision for two non-spinning black holes with a modest mass ratio of 1.6 and starting from a very small separation. So this is an example. So this tells you what the world tube of these horizons are. So initially I have the purple and the red cylinders. They represent the world tubes of the two individual black holes. So initially, as you can see, they are disjoint and there is no common horizon. But as the evolution proceeds, at a certain time, which is called T bifurcate here, a common horizon is formed. That is a dashed black surface. And that then splits into an inner and an outer part. The outer one is the one of interest to us. That is the apparent horizon. That's shown in blue, and that settles down to a final black hole, while the inner one then becomes highly distorted and merges eventually with the two individual black holes. And this is fun to show in a movie, so I will show a movie now. So let me just share this other screen for a moment, and so that you can see the movie. So just give me a second. So this is then the movie for the showing the same plot I showed you, but just now in terms of movie. So then I have the two black holes that again are represented by these marginal surfaces. So they evolve, a common horizon forms that splits into inner and outer part. The inner part becomes really complicated. It has then self-intersections and so on. So that's all nice, but the interesting part for this talk is the surface in blue. So that is just the common apparent horizon, and we can track it all the way from when it's initially formed to when it settles down to a final black hole. So now there's of course many features of this scenario which I could give a talk on independently, but I'll just focus in this talk upon the common apparent horizon. So I'll now go back to sharing the slides as well. Okay, so let's go back to the slides. So now the one aspect I want to tell you about is so I told you that the final black hole when it's formed is very distorted and very dynamical. How do we check that? So the easiest check is to look at this area, right? So we expect that this black hole is growing because radiation is falling into the black hole. So in this plot, just focus on the blue curve. So this shows the radius of the final black hole as a function of time. So on the x-axis is time in the simulation time coordinate. On the y-axis is the radius of the final black hole. So the black hole is formed exactly when the final black hole is formed when the blue curve starts. And you can see initially it is growing quite rapidly in area, then it settles down and reaches a plateau, and at the end, area becomes really very, very constant. So in the initial parts, the black hole is very dynamical, it is highly distorted, and it is growing quite rapidly. So if you were to imagine that you can treat the black hole just at formation as the perturbation of a curved black hole, then that just simply cannot work. So just to say that if you expect that any of the analysis based on the Quasi-Normal mode frequencies, that is based on a perturbative calculation, so in principle at least, that should not apply to the black hole horizon just when it is formed. So that is just the fact that I want to take away from this. Okay. So now the important point, again, this was emphasized by Sukanta in his talk yesterday, is that so there are interesting correlations, however, between what's happening on the horizon and what is happening at infinity for the observed waveform. So this means that you can infer from what, if this is true that these correlations are there, then based on what you see in the gravitational wave signal, then you can infer what is happening at the horizon itself. And then Sukanta gave this example with the spiral in his talk. Now the same is in fact true for the final black hole as well. So in fact that leads to contradiction then, right? So based on the results by EC and Giesler and others, so if you believe that the waveform at infinity is well described by the higher overtones just after the merger, so that might lead you to conclude that in fact the black hole at that point is well described by linear perturbation theory. And we see already from this plot here, just from the area increase, that in fact that is not the case. The black hole is not a perturbative curved black hole in that case. Okay? So you already get what you might think is a contradiction at this point. So let's analyze this. So let's see what is happening at the common apparent horizon, and let's look at geometric fields at this common horizon, and let's see how they decay and reach equilibrium. So again, as Sukanta mentioned in his talk, the important point here are the shear modes. So you look at the shear of the outgoing normal at the horizon, you decompose that into different modes, and in this case, because we have really axisymmetry, this decomposition is really well defined. So given this complex function, which is the shear on the horizon, I can decompose it into different modes, defined by a quantum number L, and that you can then compare with with the quasi-normal modes. Okay, so let's look at then what happens with shear. So these are plots of different shear modes. So starting from the top left to the bottom right, it shows you what the L equal to 2, 3, 4, 5, 6, 7 modes of the shear is doing as a function of time. So for each of these plots, it's on a logarithmic scale. On the y-axis shows you the mode amplitude for the corresponding mode, and the x-axis is the time. And these plots all start when the common horizon is formed. So if you look at the top left plot, for example, so sometime at very early times, you get just very rapid damping. And then as you cross roughly 10 m on these plots, you get oscillations, which are then, you can see that it's a logarithmic scale. The oscillations appear at these inverted spikes. So those are then the oscillations. And the same is then seen for all of the other modes as well. So if you look at the L equal to 3, 4, 5, 6, and 7 modes, the same behavior is true. So you get this initial period in which you have rapid damping, and then you have a somewhat later period in which you have oscillations and a slower damping. So then you say, aha, that's interesting. So based on these oscillations, I can compute what the oscillation period is, and that should tell me what that should hopefully be connected to quasi-normal mode, oscillation time. And then if I can fit also the damping with the green curve at the late time, so that tells me then what the decay rate at late times is, right? And I will do this analysis at a sufficiently late time, in this case, after the vertical line marked T2 in these plots. Okay, so after that time, I'll fit these with a damped sinusoid, and I'll extract the oscillation time and the damping time based on that, and compare that to the quasi-normal mode frequency and damping time. Similarly, for the very early times, so something very early to the left of the vertical line marked T1, so I would fit that with a damped, again with a, in that case, there are no oscillations here evidently. So then the obvious strategy is to just fix it to just a damped exponential function and to estimate the damping time from that. Okay, so this is a very straightforward procedure. Let's apply this and then see what happens. And by the way, I should say that the same analysis, the same behavior is seen exactly for the multiple moments as well. So for this final black hole, you can compute again, can decompose the scalar curvature on the black hole in terms of spherical harmonics, and this gives you a set of multiple moments, which are the mass multiple moments. And these satisfy exactly the same kind of behavior. So you get the initial time, which is just a rapidly damped function, and then later time, which is a damped oscillation. Again, this same fits with the red and the green straight lines. So let's do this fitting procedure and let's see what values we get. Okay. So again, just to be very clear, so the model is the following. So this is the first approach I'm going to do. I'm going to do a more complicated one in a minute, but this is just the first very simple approach that one might do. So this is to say that before a time t1, the function, the sigma L for any of these modes is simply an exponential function. So this alpha 1 in that case is real, so it's purely a damped thing with no oscillations. While after some time t2, we want to get a complex frequency, so let's say that the function is a damped sinusoid. Okay. And again, to emphasize, these transition times t1 and t2 here are not equal, so we want t2 to be as late as possible and t1 to be as early as possible. And based on this, I want to estimate what the oscillation frequencies are at late times and at early times. Okay, so then these are the values. So in this table, so the first column is the L mode. So by the way, I should have said that in this case we have axisymmetry, so the M modes don't enter. So I just have a different L modes to consider here. This is from L going from 2 to 7. And then the second column shows you what the damping time is at the very early times. So that is alpha 1 for the different L's. So that's minus 0.578 and so on, those different values. While the next two columns are the real and imaginary parts of the frequency at late times after of t of 20. Okay. So those are the times I want to compare with the fundamental quasi-normal, the Schwarzschild QNM frequencies. And in fact, they had really good agreement. So if I look at the third column on this, in the first table, so I get the real part of alpha 2 is 0.377, 0.602, and so on. And to compare that with the QNM frequencies for a short-shell black hole for the fundamental, for the zeroth overtone, so we get values very, very close to that. Okay, so by L equal to 7, we don't have enough accuracy, so you shouldn't trust that, but up to L equal to 6, things look really good. And in fact, the same is true also for the damping times. So for the damping times, you get, again, very good agreement with what we obtained by this very simple fit, and what we expect from the short shell QNM frequencies. So everything is good so far. And right, so now what about the, so essentially, so this confirms that the late time decay is dominated by the fundamental QNM mode. And in fact, this is true not just for the shear, but also for the multiple moments. So really, we have a lot of evidence that things are really very well described by the QNM frequencies at late times. But what about the early time? Now, that is an interesting question here, right? So we want to see that, well, in this column, in this table, is the alpha 1, does that correspond to any of the higher overtones? And it would be nice if they were, but sadly they're not. So at least from this first simple analysis, you see that, in fact, these best fit values do not agree with the higher overtone decay rates. If you look at the publication, you'll see the tables, and then you can just confirm this for yourself. So we have, from this simplistic analysis, no evidence for any higher overtones just after the merger. Right? So that is the first thing. But of course, what Giesler and EC did was more sophisticated. So they didn't just assume one damping time, but they tried to fit all of these functions by combination of quasi-normal mode frequencies. So this is now what we did. So this is ongoing work. So the results I'm going to show are preliminary in this case. So what you can try to do again is at the horizon, you can try to fit the shear modes and the multiple moments by combination of these QNM frequencies. So take a model of the form of amplitude times exponential of the QNM frequencies to include the number of overtones n and see how well you can fit the data. And the question is, does the fit improve? And if so, that is then strong evidence that in fact, also at the horizon, you get these higher overtones, even though the black holes that we just saw at that point are not perturbative. They're far from Kerr at that point. So this is an example of what was done. So in this case, I'm looking, this result is again is preliminary. This is work done mostly by Pierre Mourier and by Chisco Jimenez Forteza. So let me just explain what this plot is. So in each of these plots, the black dots represent the data, the shear one that you just saw. And in this case, I'm looking at just the L equal to 2 mode of the shear. And I want to fit that by across the whole time, not just at late times and early time, but across the entire duration by a combination of overtones. If I do this fit, including no overtones, I get a very bad fit. That is the top left panel in this sequence of plots. Then I include the second overtone, so the n equal to 1, the fit gets better. I include the n equal to 2 overtone, the fit gets even better. And then, okay, after that is diminishing returns. So you can just say that once you include 2 overtones, and you can fit the L equal to 2 mode really well here. Okay? So amazingly, even though the black hole is not really very isolated, it is highly dynamical, just based on this brute force numerical fitting procedure, you can say that you can fit the data well enough, including enough overtones. And the same is true here also for the L equal to 4 mode. So again, you see that in this case, you need more overtones. So you need to go to n equal to 4 in this case. But including enough overtones, you can really obtain a good fit of this data. Okay. So this really confirms that the initial analysis we did was quite simplistic. And in fact, you need to include these overtones to get better fits. And in fact, the fits do improve as you include the higher overtones. So now, what should we make of all of this, right? So first of all, I should emphasize that there was no reason any of this should have worked at all. So in this case, if you follow this closely enough, I have not rescaled any of the simulation time. You know, the simulation includes gauge conditions and everything. So it's a particular time coordinate, a particular slicing condition and things like that. So there is no reason that any of this should have actually agreed with what we see at infinity with the waveform. So that's the first sort of interesting thing. So Okay, ignoring that for the moment and assuming even that any of that, all of those concerns are sort of a typical theorist concern and don't really concern us here, even then should we believe in the higher overtones? Well, the pro is that the fits do work much better if we include the higher overtones, so that is a very strong argument. But on the con side, you have that, again, as I said, the black hole is not in equilibrium at these early times, so black hole is growing significantly, so you can't interpret that as a perturbed short shell black hole in any sense of the word. You could try to include higher order sort of perturbations, and maybe that is a way to explain it, but so far that calculation doesn't exist. So now the other thing on the con is that, well, are we just fitting a function here? So could we fit any such function, which is this feature of the damped sinusoid, by combination of the Q and M's? And that is probably true. And finally, as you might have noticed, for the higher overtones, we don't restrict the oscillation frequency at all by this analysis. So if you go back again to any of these plots, at the very early times, you get almost no oscillations, right? So in fact, that is true. So for the higher overtones, you get very little information about the oscillation frequency, even though you can measure damping time pretty well by this procedure, but not the oscillation frequency. So perhaps this is, again, you're just fitting functions here and without any deeper physical meaning. But again, if you go back to the cons, right? I mean, if you had one good reason, you don't need to give three sort of moderately good reasons, and you can always go back to the case, well, the fits do work much better. So unless you have something which is sort of more plausible, then we should just go with the fit and assume that the higher overtones to explain this behavior that we see here. And what you really need are, in fact, calculations from first principles, or rather better arguments for why do we expect these overtones to be present, both for the black hole horizon and also for the waveform at infinity. So on this sort of open-ended note, I'm going to conclude. So I'm going to say that that observation of gravitational waves, so it gives an entirely new way for testing GR. So, and especially, again, for the people not in gravitational wave analysis yet, doing different fields or getting in the field, there's a lot of open data and there's a lot of things that can be done in the next, now and in the next years. And in fact, there's already several important results, but I would say that to really test GR with high precision and to hope to find deviations, you really need to go to sort of high precision GW astronomy and to the next generation of detectors. So and this will happen, in fact, with upgrades to LIGO Virgo detectors and hopefully a third generation detector and hopefully even LISA after that. So again, the prospects for black hole spectroscopy are promising. And in fact, as I convinced you, so to really understand this problem involves a combination of observations, numerical simulation, and theoretical calculations. So I'm going to conclude and happy to take any questions.
Thank you very much, Professor Badri Krishnan, for such a nice talk. And so it's now time for questions, and it's now open to audience to any questions they may have.
Badri, wonderful presentation. This is Partha Majumdar.
Thanks.
I would still continue with this idea that, you said it already, that there's no proof, for instance, the GW 1509, that you had a black hole binary in spiral. The area increase in GR specifically applies to black holes. So suppose you didn't have a black hole binary in spiraling, then of course the area increase considerations would change, wouldn't they?
Yes, indeed. So in fact, that is one of the motivations, right? So what are the plausible reasons that the area may not increase based on the sort of the simple arguments they're relating the area to the mass and the spin? Well, one could be that the conditions assumed for the area increase law proofs do not hold. For example, the null energy condition does not work, for example.
Right.
So that would mean sort of anomalous flux of energy during the merger. Another reason might be just what you said, because these objects are not black holes, so there is no reason to expect the area increase law to work. So indeed, yes. So any of these could be plausible sort of explanations for if we do see a deviation from the area increase law. Yes, you're right.
We've been doing some work on trying to get a lower bound on the remnant of the post-merger remnant of any kind of binary system, be they black holes or gravastars or what have you. And I think one can derive them, but of course there's some other considerations. I just wanted to say that maybe there's still a lower bound on the area of the remnant, be it a black hole or whatever else. And if you can actually measure areas like you pointed out, then even if they're not black holes, maybe there's something there, right? I mean, it would be useful to have such a thing, wouldn't it?
Yeah, absolutely. So I'd be really interested in that. So I'll definitely be happy if you want to talk about it after.
Okay, sorry, just another question about the last part, which is very interesting, about the fact that as you went earlier and earlier towards the merger, you actually did not find oscillations. And this is perhaps the indication that strong gravity is too strong in that region, isn't it? I mean, oscillations start when things are actually cooling down in some sense, when things have happened and then there's a decay. Wouldn't you say that? Sorry?
Yeah,
Hello?
so that, I'm just thinking about your comment. So yeah, so I don't, is that true? So I don't know the answer to this. Is that true in physical systems normally? So if you have sort of rapid decay or very far from equilibrium behavior, that you don't get oscillations? I don't know the answer to that. If that is true, that is also interesting.
Yeah, I mean, normal systems begin to oscillate only after they have been in some sort of quasi-equilibrium, isn't it? Of course, gravity is different. I mean, as you correctly pointed out here, the nonlinearities are playing a major role, and the diagrams are extremely, on this context, I wanted to ask you, has anybody tried to write down a metric for a two black hole system?
No. So people have tried. So in the PN approximation, you can, but if you want the near horizon behavior, no.
Right. Okay. Thanks very much. Wonderful presentation, Badri.
Professor Sham has a question, please.
Badri, very nice talk. I have a small question. In your simulations, you can change the masses, right? So you can.
Yes, indeed. So,
in your simulations, you can change the masses M1 and M2 and take them to be large. Is that true?
yes. So in this case, the masses themselves are just a scale. This is no scale in the simulation, right? So the total mass just sets a scale overall. So
right.
The important point is just the mass ratio. Yes.
Right. So what I want to consider is that if the two black holes which are merging were already supermassive, then the curvatures are very small at the horizons anyway. Now when they are merging, that is different from small black holes. So can this be simulated by taking the total mass of the final black hole to be supermassive?
And as I said, so this simulation already include that because the total mass I can make it anything alike. So total mass is just a scale for the whole simulation for the time and for distances.
Oh,
so in fact, yeah, the result will exactly be the same. So important feature is just the mass ratio. So total mass will not affect this behavior that I've shown. Simulation is inherent in the scale of a total mass.
So is this the limitation of the simulation, or because physically I would expect it to be different for very heavy mass black holes versus lighter black holes?
No, in this case, it's just that the ADM mass just sets a scale for length and time. So it's a fundamental thing. In at least if you don't have matter fields, it's just vacuum GR. So the total mass is just a scale. So the same behavior is seen for no matter how massive
so
the.
always get the same effects. I see. That's
exactly. So that's again it's an important comment because this means that these effects are non-perturbative. So no matter how small the curvature at the horizon is in sort of physical units, if you like, you will still have these effects. But in geometric units, then you see what's happening.
I see. That's very interesting.
Yeah.
Thank you.
Are there other questions from the audience? Okay, there are two questions in the chat box. So one is from Syed, who is asking, among the in-spiral merger ring down parts of a gravitational wave signal, which one gives the most information about the nonlinear effects of GR?
Yeah, so I would say that the merger there's nonlinear effects, as I said, in all of them. The PN calculation do include nonlinear effects, but the merger is where these becomes really important. And also, in fact, the memory is also, the contribution is the most for the merger as well. So if you were to sort of track the memory, how it changes as a function of time, the largest increase would be at the merger. So in fact, yeah, so the answer is the merger.
And he also has another question, is nonlinear memory effect related to quasi-normal modes?
Not really. So this is nonlinear effect. The memory effect is just a sort of the gravitational wave energy flux also sourcing the wave itself. So no, it's not related directly to the QNN though.
Then there is another question from Paulomi Datta Roy, who is asking how are the coefficients fixed by fitting the overtone modes to the signal?
Oh. So am I still sharing the screen? So your question is about how, can you see the screen still? The slides are
Yes.
still being shared?
Yes.
Okay. So yeah, so I take it your question is how are you doing the fitting and obtaining these fits, right, for the amplitudes?
These ANL coefficients, how do you fix?
It's going to be a least squares procedure. So there's also an MCMC procedure, and you get similar results. So you can use any favorite procedure you like to fit the model with the data. So all of them give essentially comparable results.
Any other questions from the audience?
Badri, hello. Can
Yep.
I ask a question? Yeah. So this is Shudipta. So the area law which you were talking about is the area law for dynamical horizon, if I understood it correctly. The MOTS. Hello.
Yes, go ahead.
Yeah. So what is this analysis proves is that the area actually increases monotonically for dynamical horizon, but for event horizon we can only prove the global area increase. So we cannot still say that the area, even since we cannot track it, we cannot still say that the area of the event horizon has increased monotonically. Is that a correct way of saying it?
So the correct way is that the test itself is only for the global area increase law. So in other words, we use the very late time measurements of the mass and the spin to get the final area. So that is the area at the very end. On the other hand, we compare that to the area at the very beginning. So in other words, this is the test itself as I presented, it is only for the global area increase law. And this applies to both event horizons and to any of dynamic horizon as you like. So at the early times, the two things coincide. At late times, they coincide. The middle, they're different. But it doesn't matter. At the early times and late times, they agree. So for both cases, we're just testing the global area increase law.
Okay, thank you. Thanks, sir. Just a question. In Hawking's proof, you can take this event horizon and take the Cauchy slices at different Cauchy slices. Then at every Cauchy slice, if you calculate the area of whatever number of black holes you have, the area does increase monotonically with that.
Yes, it does increase monotonically. Yes. So that area increase law is a monotonic increase. Yes.
So you do see that, right?
Yes. I mean, we don't track the event horizon in simulation, but that has to. Well, that's exactly
for event horizon, but yours is not for event horizon. But I thought in your paper you also mentioned that these results are valid for apparent horizons too. I mean, this marginally MOTS surfaces.
Yeah, so that's a topic for entirely different talk. This takes too long to explain in detail. The short answer is no, it's not true. There's a very short duration of anomalous area change just at the very heart of the merger. So it is generally true for the cases that we looked at, but in detail, it is not in fact true.
Oh, I see. Okay. So
that's an interesting aspect which you're still struggling with, but that is what it is.
Okay. So one can't compare directly. Okay.
Yes, so I would say that if you really want monotonic area increase, that is very hard to do also observationally.
Yeah.
So you have to sort of obtain the area at each intermediate time. That is, I don't know a way to do that. So I would say the global area increase law is something that you can hope to address sort of observationally.
Okay.
Are there any other questions?
Hello.
Yes.
Hello. Hello, sir. I have one question. How can I write the metric of the rotating black hole as a dynamical black hole merger? Is it possible?
I don't think so. I don't think it's possible. So you mean that can you sort of modify the metric of a rotating black hole to describe the merger, right? So if that was a question, I think that is not possible. At least not everywhere in space-time. So you might sort of get away with it sort of at large distances and so on, but if you really want to go to the sort of strong field region, I think it's not possible.
Thank you, sir. Okay.
I think there is one more question in the chat box. So how, it's from A Chatterjee, how one may use it, the law I think you mentioned, to prove the flux law for horizons.
Could you repeat that? What could I use to prove the flux law for horizon? Could you repeat the first part?
Yeah, the area increase proof that you provided, whether you can use it to prove the flux law for horizons.
Well, it's the other way around. So at least in this framework of these dynamical horizons, you use the flux law, another condition, to prove the area increase law. And while for the event horizon, it is the other way around. So there's a proof for the area increase law. So that is simply true with some condition like cosmic censorship and the energy conditions. And you can show that the area of the event horizon at a later time must always be larger than at an earlier time. But for the event horizon, what you don't have are the fluxes and at all times.
Any other question from the audience?
So, Badri, this is Abhay. I unfortunately missed the first part of the talk because it was way. Hello?
Hello, sorry, I missed the first part of what you said about.
Yeah, okay. So, you may have covered this already, in which case you don't have to say it again. But if you have not, then perhaps you could say a few words about what one expects with LIGO India coming online. What more things one would be able to do, what improvements one can do, and secondly, what one expects just from the 3D earthbound detectors, how these things would improve. Just your vision and just a few words, that would be helpful.
Yeah, so for the LIGO India, the most important thing is sky localization. So in any of these area increase law tests that I talked about earlier, so the sky localization does play an important role. So if you're assuming that you get the sky localization based on unmodeled search, for example, and the better you have that, the better it becomes. So for that test which I mentioned, I think the sky localization would play a very important role. Of course, improving sensitivity helps everything overall, but specifically for LIGO India, the sky localization really matters a lot. And the same thing, but once you have the sky localization, once you have LIGO India working, you have a large baseline between the different detectors. After that, it is simply a question of the detector sensitivity improving. And then I expect that by the time, about 10 years from now, let's say from the intermediate generation detectors between ET and LIGO, that you could actually hope to get a few events to test this black hole spectroscopy scenario. But definitely for ET and then for Cosmic Explorer, I think I'd be quite optimistic on that.
Thank you.
Any further questions? I just have one small question. So you talked about the equivalence of the quasi-normal modes and the shear, the time evolution of the shear at the horizon. But you also know that the quasi-normal modes have a close connection with the perturbation around the photon sphere. So does your result suggest that there is again a connection between the photon sphere and the shear at the horizon? So would you comment on that?
Yeah, that's a good question. So we haven't addressed that yet. So for that, we'll have to look at sort of what is happening to, if you want, photon spheres, or I would generally say I want to look at what the space-time metric is doing near the final black hole. So that we have not done. So to address your question, we would have to do that. And there's also other suggestions for how you might extract information relevant to Quasi-Normal modes. If you look at effective potential, how it changes just when the common black hole is formed, for example. So those are all very good ideas. So we're starting to do that, but we haven't done that yet. So the short answer is no, we have not done that.
Okay, thank you very much. So if there are no more questions, let us thank Professor Badri Krishnan and all other speakers of this session. And
Thanks also to all the organizers. So I think also an applause for the organizers.
So I guess it is time to close this online workshop, and we had very good participation from people throughout India and also from people abroad. We had very good speakers starting from Professor Badri Krishnan, then Enrico, P. Ajit, and the previous day we had Vitor Cardoso, Sukanto Bose, and KG Urun, along with the special colloquium by Professor Abhay Astekar. And all the participants cooperated with the seminars and they asked various questions. So we hope we are all enriched by the knowledge that the speakers gave us, and also through the questions that we have learned many things. And I guess we'll be doing this kind of things in the future as well. And I hope many of you will join us again in the future to make it a success. And I would like to thank the organizers like the IACS authority and also the IIT Gandhinagar authority for make this program a success. And also the directors and deans of the respective institutes who have helped us in performing this well. So I guess with this closing note, we can end this workshop, and thanks to all the speakers and participants to come to this workshop and make it a success. So thank you very much. Have a nice weekend.